I've also put the configuration in for how to create the bird server for the IXP and for the other ISPs on that website. Okay, so my name is Diarmuid O'Brien. I'm a lecturer in Makerere University. As it's obvious, I'm not Ugandan, right? So I'm Irish. So my background is as a CTO and an ISP in Ireland for a number of years before I came to Uganda. And when I came to Uganda, I was met by a lovely woman called Dorothy Okello, who is a lecturer in Makerere, and she dragged me out there to work with the NetLabs Research Centre. So the NetLabs Research Centre is in Makerere University. So what I'm going to talk about today, I'm going to look at, I was asked by the guys in MikroTik if I could talk about tips about mistakes that could be made when you're setting up an ISP or in the early stages of an ISP. I suppose, unfortunate that when I was in my last company, we started off with no network, a CTO, a CEO, and a chief financial officer, and no network. And then we bought 10 companies in about 6 months. And I had the task of trying to make all those networks all come together. So we got all the different types of networks. So I can go through what's good, what's bad from experience. I'm going to look at the inter-autonomous system routing. It probably would have been better if this presentation had been before the last one, because I'm kind of going through it at a more simpler level than the EOIP presentation. I'm going to talk about internet exchange points and the benefits of them. I'll talk about BGP peering configuration, and then finally how to configure the BGP peering to an IXP. So I was thinking about this when I was asked about, well, the different types of ISPs. So I decided to categorize into 5 basic types. Now there are going to be different, other bits that are in between, and a little bit of this and a little bit of that. But basically there are 5 basic small ISPs anyway, as you grow to becoming a larger ISP. So the first one of them, I call it my kind of NAT ISP. This is where somebody has decided that they want to make up a wireless ISP, for example, and they're good with radios. They know they can put a radio on a roof and they can point it at an access point, and they've got a high building in a town, and they point their radios to that high building. And their problem is, how do I get connected to the rest of the internet? So what they do is they buy themselves a fiber connection or something from a provider, and they put on a NAT gateway router. And basically they're NATing for all of these customers. So the customers are getting private address space IPs. They're being NATed onto a connection to an upstream provider. So for all intents and purposes, they have extended the green ISP here. They've extended their network inside the other network. These guys do not have an ASN. They do not have IP addresses. They just have private IP, which is very, very bad, because the customers are getting a private IP address in the first place. If they're going to have a little router at home, then they're going to be NATing on NATing, because they're NATing on their own router, then they're NATing on the ISP, so it's bad. The ISP finds it extremely difficult. They can't multi-home, so they can't connect to another ISP for resilience. If they ever decide they want to address their network properly and connect to another ISP, then they have to go and re-IP the whole network. So this is kind of, I would consider, the worst model of an ISP, okay? The next one isn't much better, but it's slightly better. It's where I've gone to an upstream provider and I've asked for public IP addresses. So they're supplying me a wholesale service. They're giving me IP addresses from their blocks. But my ISP does not have an ASN. It is part of the larger ISP's ASN. So there's still only that ASN there, 5333. And this network, the yellow network, is the ISP we're talking about, and they are part of the green network as well. Okay, the next type one is getting better. This is where we decide to be a full ISP ourselves. And in Africa, the key here is Afrinic. Afrinic will assign ASN numbers, autonomous system numbers, which makes our network autonomous. We can then connect to other autonomous systems. So we look for an autonomous system number, and we look for IP blocks, IPv4, IPv6 blocks. In this case, you'll note that the green network and the yellow network are not connected. This network now has its own ASN, so it's an independent ISP. It's using this tier 2 ISP up here to get transit. Okay? So this is a much, much better model, because the day I get kind of cheesed off with the green ISP who are charging me too much, I just simply have to make a connection to another ISP and switch my traffic. The customers don't even get an outage. So this is a good model. I can also decide to connect to another ISP anyway and create routing such that if one fails, the other one stays up so I don't lose any connectivity. My next model is what I would consider the best model. That's where I also make a connection to an IXP. I'm going to talk about IXPs in a few minutes, so I'm not going to spend long here. But basically, I have a peering with a transit provider to get to the general internet, and I have a peering with the IXP locally to handle local traffic and keep it local and keep latency down. So that is my favored model for an ISP. And the last model I would consider the virtual ISP. I don't know whether it's that common in Africa, but it's very, very common in Europe, where the brands like Sky, Tesco, shopping centres who want to pretend they're an ISP, they will buy the core network pieces of being an ISP, and then they will basically buy access from other providers. So they're like the cuckoo in the nest, if you like. So if this is, say, Kenya Telecom or the general ISP, they will buy services off them, and they will supply them with routers which will establish VPNs generally back to a tunnel terminator on their network, so that the customers get IP addresses from the Tesco network or the Sky network. They will appear, for all intents and purposes, that they're connected to this as an independent network. The big advantage for the Tesco and Sky is they don't care about installing. They outsource that to the company who have the real network. They don't care about rolling out hardware, because that's the other person's problem. So they usually then try to layer on top of that additional services like TV services. So it's very common with TV companies wanting to layer their products. So there are my 5 basic models. Now you may find that there are some mix of these. You may have an ISP who's a wireless ISP who is using fiber network from somebody else. So they may have a little bit of the virtual network on their network to get to customers that they'd otherwise lose. Okay, so what is an autonomous system? And what is inter-autonomous system routing? So here is a kind of a basic picture of 2 autonomous systems. They have an autonomous system number, and there are 2 types of ASN number. There are 16-bit and 32-bit, and there's nothing really different between them, except one is longer than the other, and the longer one was brought in because they were running out of 16-bit ASN numbers. So inside the autonomous system, the owner of the autonomous system, the ISP, is entitled to use whatever interior gateway protocol they prefer. They can use OSPF, they can use ISIS, they can use RIP if they wanted to. Static routes if they even wanted to. And then they interconnect to other providers using eBGP, external BGP, Border Gateway Protocol. And that's the standard protocol being used on the internet since the 1990s, since 1994. I've also shown iBGP links, and they're interior BGP links, and they're really used to connect border routers. So if I have 2 border routers connecting to either one other ASN or multiple ASNs, I can connect my border routers using iBGP so that the routes can be shared between those routers using BGP. The 3 kind of main elements to a BGP packet are the origin. What is the origin of the path? The AS path, that's a list of all of the autonomous systems that this particular route has passed through. So as a BGP message passes from one autonomous system to the other, the local ASN is prepended to the list of ASNs. So when it gets to the end, they will have a full list of all the ASNs that this particular route passed through. And then the next hop, what IP address should go to next? So there's the router itself has a BGP finite state machine. Now this is a fairly simplified version of it, but it's kind of important, particularly for troubleshooting. We'll often see someone would ring and say, oh, my router is showing that it's connected, okay, or it's in connect state. Why is it not working? Well, the BGP state means that the state machine must be in one of these states at any given time. And what happens when you plug in your cable, and if you've configured on both sides, is it will quickly jump from an idle state to a connect state onto an open send state, open connect, open confirm state, and finally establish. But that'll happen really quickly. It'll go through those. And then if there's a fault at any of those states, like for example here, it's not able to go to open confirm, it will go to TCP failed, and it will stay in an active state. So you may see on your routing BGP peer print, you will see that the link is in active state, and you think, okay, that's fine. No, it's actively trying to make a connection, so it's not actually fine. It's only fine when it gets to an established state. So this is just looking at the different messages that go over and back, but the main message to look at here is the update message. And as you can see, the things I was talking about, the AS path, the next hop, and there's the NLRI, or the network layer reachability information, is the network that we're trying to route. So looking at an actual packet, so this is, I've obviously ignored the layer 2, the layer 3, and the session, and I'm really looking here at the application, the BGP. So in the update message, it gives you the attributes for this particular route. So the origin is always IGP. The path attribute then, if AS path is 5999, that's the AS number for this particular route. The next hop is the IP address, okay? And then we have the network that's been routed. And for IPv6, it looks very, very similar. Very, very similar, in fact. Difference here is that it'll also show a local scope route. So here's the local scope, as well as the actual global scope. Okay, so that's a kind of a quick look at BGP. So where does IXPs come into? The IXP is a really good idea and has been around since about 1992, started in Sweden. And a lot of people think, and I heard this in Ireland where you have smaller ISPs going, oh, the IXP, that's something for the big boys. That's for Aircom or for Vodafone or for that. It's not for me. I'm too small to connect to the IXP. I would say that's not true. In my network at home, when I told our CEO that I was paying to join INEX, and it's a lot more expensive than joining UIXP. I don't know the price for joining the Kenyan IXP, but we're free at the moment, but not for much longer. But the INEX was a lot more expensive. And he was saying, why are we spending this money? And I said, well, we're going to route. At least 30% of our traffic will go off transit, which we're paying heavily for, and will go to the IXP. And because we're lucky in Ireland, we have a lot of content providers in country. So he didn't believe me, but he said, look, you're the CTO, you make the decision. So I did. And he came to me afterwards to say, well, was it 22%, 23%? And he was kind of smiling, and I said, actually, it was 42%. So we got 42% of our traffic that had been going to transit jumped to INEX. So it was massive for us. It was a big, big reduction in cost. And over time, of course, the cost caught up because transit was going up and up and up. But relatively, our costs were being kept down because, over a third of our traffic was going to the exchange. So this is a makeup of the internet, I would say, of 10 years ago. There's been a transformation in the internet over the last 10 years, and a lot of people haven't really noticed, but there has been. But this was the original model. The idea that you would have access tier ISPs, or local ISPs at tier 3, they're the ones that have customers. They're the ones whose houses are connected. Above those, we have tier 2s. These are ISPs that provide services to ISPs and to large enterprise. So a bank might connect directly to a tier 2. A small ISP connects to a tier 2. And then tier 1s, they're kind of the very large ones that interconnect the continents, if you like. And then connected to those, we had our content providers. You had your YouTube, you had your Facebooks, all of those at the beginning. But what problem do you remember from 8 to 10 years ago with YouTube, for example? I'm a big Munster rugby fan. I live in Uganda. I can't watch Munster rugby on, the odd time I can watch it on DSTV now, but generally speaking, I can't watch it on DSTV. So I have to pretend I didn't see the score, wait until Monday night, get onto YouTube, watch somebody has put the match up. But 10 years ago, I would have seen this circular thing going on all the time. Buffering, 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 buffering. You don't see that so much anymore. And that's because this has changed. So what was the problem? Well, the problem was that, generally speaking, if we had these consumers here, and one of them was trying to connect to this large enterprise, let's say in Uganda or in Kenya. So somebody in here in Nairobi was trying to connect to Standard Chartered Bank. And both of those companies have their services here in Kenya. What was very likely happening was that the traffic would go to the local ISP, who went to a tier 2 ISP who happened not to be the tier 2 ISP supplying this large enterprise. So their traffic headed out beyond the sea at Mombasa, into the Middle East, through to Europe, into links in London, and then got switched at links in London and came all the way back. So your traffic was going from Kenya to London and from London back. So you can see, if I told you that I wanted you to go from here down to into the middle of town, you wouldn't go via London, right? You'd go in along that lovely big highway they have there outside on the road, yeah? So why would you put your packets that way? We're getting latency, there's cost because the transit has to be paid for, and the growth of the ecosystem within Kenya then doesn't have that same oomph if you had your traffic local. So what the IXP does is it allows the local providers to connect together on a switch. It started out as a switch with two providers, Telia and Tele2. They were the two providers in Sweden connected to a single switch provided by Sunnet. And in the UK, the second exchange in London was 5 providers connected to that exchange. So it started very small and it simply was a switch and everyone peered with everyone else. So now my traffic comes to the routers here and they make the decision that actually it's not efficient to send it to Europe. It's much more efficient to go to the IXP and then down to the large enterprise. And in a lot of cases, the large enterprise will actually have their own connection now with an IXP. IXPs are no longer the preserve of ISPs. It's ISPs, large enterprise, banks, etc. Anyone who is an ASN. So we reduce our latency, reduce costs, and we increase our autonomy in the region. So what the IXP does today, the IXP has too many members to just have a switch and everyone peering with everyone. Because every time you peer with everyone, you have a lot of peers to set up. So it's much more efficient if the ISP provides a root server. And a root server is a bit like a router. It takes in routes, and a route comes in for this ISP, for ISP1 into the exchange, and the root server here sends that route on to all the other ISPs. But unlike a router, it doesn't prepend its AS to the AS path. So if it was a regular router, it would say, okay, what ASM am I in? I'm in ASN 37123. I'll prepend that to the path, which is AS 2434. So when it gets to the one at the end, it should see in the AS path, it should see 37123, and then it should see 2434. But when it's a root server and an exchange, it doesn't prepend this. So for all intents and purposes, this ISP receives the route as if it got it directly from this one. But it doesn't have to peer with this one. It just peers with the root server. Okay? So looking at configuration. So for start off, we're going to look at configuring ISP1, ASN 5111. And we're going to do a peering configuration with this tier 2 ISP called ISP3. We're not going to look at the configuration at this, but we're going to look as we are the ISP connecting to an upstream provider. Now the configuration for this is in those files that I talked about on the website. So if you wanted to rebuild this testbed or something, it's fairly easy to do. So we put some IP addresses on. So we have IP address here for this client representing all the customers. We have 199.1.1.100 and 2A99:1:1:100. So there's our IP on the machine representing the customers of this ISP. We obviously have .1 and ::1 of that particular subnet or that network as the interface IP here. And we have 199.5.5.11 and 2A99:5:5:11 as the IPs on the network through to here. And I've done it nice and simply. I just used /24s and /64s. I know because the point-to-point link we should be using a /30 or whatever, but just for simplicity. The other thing I've done is I've created a loopback interface here, and I've created a loopback interface here, and I'll explain why I've done that when we get through to the configuration. So the first thing anyway, I'm configuring IPv4 and IPv6. So the IPv6 package is not enabled by default on the MikroTiks. So to enable that, I run the command system package print. It shows me all the packages and I see an X beside IPv6. So I simply do system package enable 2 because it's package number 2 and it enables it. Okay. I then default the box. So I'm system reset configuration, no defaults is equals yes. I don't want the MikroTik defaults which just confuses my configuration later on, so I clear out all of those, and it reboots. And the first thing I do, particularly in a test bit, is I give the box a name. So system identity set name ISP1. So when I'm working on it later, the prompt in the shell shows me the name, so it's kind of easy to work with. The next thing I do is I create a bridge, and I call it Loopback 0. If any of you are Cisco trained, your loopback is there by default. And a MikroTik, it's not. The loopback is very, very handy. So why would you have a loopback? So if you take a router and it has got 5 routes into the router, and I use the IP address of one of those routes to represent my connection to that router, and should that physical interface go down, not alone has that interface gone down, my link to that router has gone down. The loopback interface doesn't have any physical interfaces. It's just routed as a kind of a floating interface on the router. So if any one of the interfaces goes down, as long as I have a pathway through one of the existing interfaces, I can get through to the loopback. But further to that, we use router IDs for routing protocols. OSPF uses it, BGP uses it. So we have to have a router ID. So when you're running a testbed, and if you route your loopback interfaces, and if your router ID on the instances for routing are the same as your loopback interfaces, it's extremely easy to figure out where routes came in the routes table. So that's why I do that. Hey, did I go forward a slide or something? Yeah, so the loopback interface, I created by creating a bridge and just calling it Loopback 0. You can call it whatever you like, but Loopback 0 makes sense. So interface bridge add name equals Loopback 0. I didn't give it an IP address as per the diagram I just had there. IP address, add address 200.1.1.1. And it's typically a /32 because it's a network, it's a host network, rather than actually having a full network. There's no need, we only need one IP address on it because it doesn't have any interfaces. And I give it the interface Loopback 0. And so I'm creating this. So that becomes a name for associated with this bridge. I then put my IP addresses on the interfaces again as per the diagram. So Ethernet 2 is getting the IP address 199.1.1.1, and the same interface is getting the IPv6 address 289:1:1:1:1. I do for Ethernet 5, I have the networks that were connected to the green network, the ISP3. So I can look at my addresses I've configured, IP address print, and I see my addresses. And if I do IPv6 address print, I can see all my addresses. So now I have IP addresses on the system, but I have no routing. So I have no routes. So what I must do now is create an instance, a BGP instance, and I give it some sort of a name. You can call it anything, Mickey Mouse or whatever you like, but it makes sense to give it a name associated with the ASN number. So I've called it ASN 5111, and the AS is 5111. That was assigned to me by Afrinic. And then the router ID is the IP address of the loopback interface on that same router. It can be anything once it's unique, but again, it's just much, much easier for troubleshooting if it matches the loopback interface on that router. So now I've created the instance. So the instance is running, but it's still not sharing any information. So I now must tell the instance, what should you share? And I want you to share the networks 199.1.1.0 and 2A99:1:1:0. They're the two networks on my client side, if you like, my customers' networks. And I want to share them with the upstream provider. So if I do a routing BGP instance print, I can see all of that stuff that I've just put in there. So all of the stuff I've just literally put in here. And if I do routing BGP network print, I can see the networks that I'm routing. So I'm routing the two networks that I described here. Okay, so we're routing to the other side, but we're accepting kind of anything back as well. So if the ISP3 is sending us routes, we're kind of accepting everything. That's not sensible. There's a lot of routes we don't need to receive back. And thankfully, there's an RFC 6980 that defines a load of networks that we should not be receiving. Okay, so they're special purpose IP registries, and they're listed nicely in that RFC. We can go pull down the RFC and see what they are. So we're going to build a filter for those. But the other things we should reject receiving our own prefix. Why would we receive our own prefix through our interface? So from outside, I should not be receiving my own prefix. Is that clear enough? The other thing I shouldn't be receiving is default routes. We're doing full routing with this ISP upstream, so why would I want to receive default routes? So I want to discard default routes, and then I'm going to discard all of the networks that are defined in 6980. And that's the minimum I should do. I'll talk about something else in a second, but we should definitely do those things. Those things will serve to protect us in some way. So I create a filter. My first filter, these two lines here, these are, as you can see, I'm creating a chain. I'm calling it in ISP3-IPv4. Again, I just like logical names for things. You could call this Mickey Mouse again if you like. It doesn't matter what you call it. And I'm saying for the prefix 199.1.1.0, which is my own prefix, discard. So anything that comes from ISP3 to my router that's for my own network inside, I say, well, actually, no, we shouldn't be receiving routes for a network I know about already because it's my own network. So we discard. And we do the same for default routes. We're saying any routes that we're receiving that are for default, we discard them. So that's the two lines in that piece of the filter. And then I wanted to create a new filter called RFC 6980. And don't worry about all of these, they're very, very easy. You just go to RFC 6980, you pull it down, it gives you all these addresses. So, it's not some fancy stuff I made up, this is stuff that's in the RFC. So we create, in exactly the same way, we create a filter, but it's got a new name, it's called in-RFC 6980-IPv4. And then, when I apply this filter, I'm going to put a line in here that says, once I've done this filter, jump to this filter. So I've kind of made it like one big long filter. I could have made it all actually one big long filter, but it's just harder to look at. It's easier to look at that, knowing what's 6980 and what are my own route and my default route. So I've created the filter, but it's not doing any filtering yet, and I'll show you that in a second. So the second set of filters I'm doing is exactly the same process for IPv6. Again, I go to 6980. It gives me all the IPv6 prefixes I shouldn't be receiving incoming. I say I don't want to receive my own network. I don't want to see default routes. And when you're finished doing this filter, jump to this filter. Okay? So now I need to apply them. So to apply them, I say routing filter, add, the chain is the one I just defined, out, no, that's wrong. I should slide ahead, sorry. So routing BGP, peer add, ISP3, so this is a peer I'm adding for the route. This is in ISP1, adding it for our peer ISP3, the tier 2 provider. The instance is my own instance name, which is ASN 5111, and the remote AS is 5333. So I'm adding a peering for this ISP3, that's the tier 2. The remote address is the IP address of the router in ISP3. And then I say my in filter is in-ISP3-IPv4, which if you remember was those three lines at the top, and then it will automatically pull in all those other lines 6980 because it jumps to them once that filter is applied. I also create an out filter. I'll look at that out filter. Yeah, I jumped past it. I'll show it to you in a second. I do exactly the same process for IPv6, and the only difference for IPv6 is you must specify address-families equals IPv6. Apart from that, it's the same, except obviously I'm using the IPv6 addresses and the IPv6 filters. I created an out filter, and it's probably not necessary, but again, I like to do things tidily. So the out filter I'm saying is only route for 199.1.1.0. Invert match equals yes. So that's saying discard everything that's not this. This is the only thing I want to send out. So I'm discarding everything but the inverted match, which is my own network. And why am I doing that? I don't want anything inside my network somehow advertising something I don't want to advertise up to ISP3. So I'm filtering only my network to advertise upstream. And the same thing for IPv6. I'm only advertising that as well. So I do that, and hey presto, I have a route. So I can see routing BGP peer print, and now I can see that 199.5.5.3, which is the other side. The remote AS is 5333, so it's there. I can see that I have a BGP route learned now. I'm learning 199.3.3.0, which was the client IPs for ISP3, and the gateway is 199.5.5.33. Okay, and it's using the default distance. So now, very quickly, I get routes learned in from that ISP. In reality, if I was connecting to an upstream provider, I'd be getting in lots of routes because I would learn all the routes they know about as well. So in my test bed, obviously, I'm only learning one. The other thing you can do is there's Team Cymru. This is correctly pronounced Cymru. Most people don't know that. This is actually the Welsh for Wales. Wales is a little country hanging off the United Kingdom on the west of the United Kingdom between England and Ireland. And the Welsh name for Wales is Cymru, but it's spelled C-Y-M-R-U. And there's a project team called Team Cymru, and they create what's called a bogon list. And what the bogon list is a list of what they call Martians. They're continuously looking at the RIPE, Afrinic, etc., finding networks that are legitimate, but networks that have not yet been assigned. So if Afrinic have networks that they haven't yet assigned, why would you be receiving them as routes from ISP3? You don't want to receive them as routes from ISP3. So they kindly provide a list of all of those, but rather than you having to configure them yourself, all you have to do is actually BGP peer with their servers. So you can BGP peer with either 65333 at port 888 or at 65332 at port 8888, and automatically they will blacklist all of those networks that you shouldn't receive. They call them Martians, as in networks that are coming from Mars, and we don't have any networks on Mars yet. It gives you a full configuration for configuration that peering there at the Team Cymru website, so I'm not going to steal their thunder. Okay, so we've configured now our transit, so we're happy, but what about the IXP? We want to connect to the IXP locally. So we're now looking at connecting, we have ISP1 connected to ISP3, and now we want to connect ISP1 to the exchange, the internet exchange. And what we should start seeing is routes coming from this ASN, which is also connected to the exchange. So looking at the IP addresses, so the exchange's Bird server, Bird is the internet routing daemon that's used by most IXPs, and its address is 199.9.9.1 and 2A99:9:9:1. What I've actually done is I've created an LXC container, and in that I have, this here is actually an LXC container that can install onto a Linux host. I have that LXC container up on the website, so if you wanted to actually pull it down and set this up, you can. I've also created an OVA so that you can do it in VirtualBox if you like as well. So that's the exchange set up. So the exchange now, I have to configure Ethernet 1 with these addresses, and I have to create a BGP peering through to 199.9.9.1 at ASN 5999. So, simple enough. IP address, I add my addresses, 199.9.11 and 2A9:9:9:11 on Ether 1. So now I have IP addresses. I should be able to ping 199.9.9.1 and 2A99:9:9:1, which is the Internet Exchange. So I create filters again, and thankfully I've already created the 6980 filter, so I don't have to recreate it again. I can just jump to it, and the same here. And the filter here, I'm basically telling the link going towards the IXP. I don't want to receive these either my own network or default routes from the IXP. Okay, it's exactly the same logic as I explained earlier on. And I don't have to show you the 6980 filter because it already exists. We used it already for ISP3. So I create my routing peer, so routing BGP peer. I'm adding the name, I'm using IXP. The ASN is my own one, so the instance is ASN 5111 is my own BGP instance. And the remote AS is 5999. The remote address, 199.9.9.1, which is the Bird server running on the exchange. And my filter now is in IXP-IPv4, and if you remember, that jumps to the 6980 filter, so we get all of that filtering. And we do exactly the same for IPv6. And we apply the same out filters for IPv4 and IPv6 again. We don't want to advertise something we don't actually know about. So now, when we look at our routes table now, we can see that we've learned to route 199.2.2.0. We do not have a BGP connection with the ASN 5222 or the ISP2. We have no connection. We've only got the connection that it is also peered with the exchange, so we're learning from the exchange about that particular route as well. So that's pretty much it. I just wanted to go through the pitfalls you might have with starting an ISP. I urge you, if you're starting an ISP, pay the $300 to Afrinic, get your ASN, get your IP block and your IPv6 block. Don't take IP addresses from another provider, because if you do, you're stuck with them. It's a small bit of effort to set it up first. As you can see, it's not very, very large amount of effort to set up those peerings. Okay, so set yourself up properly with a transit provider. And once you are happy and you're running with one transit provider, connect to another transit provider. Have two. Do resilience. So if you have a problem, one has a problem, you're still on. You're not trying to tell your customers that it's not my fault, it's Safaricom's fault. Connect to your local IXP. Keep your traffic local. Another thing that IXPs have come to do in recent years is hold caches. So you'll find Google's GGC cache, Akamai's cache, all of these caches being kept at the exchange. So you get the benefit of all of that downloads that have been done by other people in other ISPs are now sitting at the cache. So you have very, very low latency from your customer to the cache. Okay, so that's a really good reason to join the IXP, apart from letting your customers access e-government services, which will all be local, and other local services as well. Keeping content local reduces latency, reduces cost. Yeah, you'll find everything at that address, or www.brian.com/MikroTik. You'll find all of the stuff I've just talked about. Okay, any questions? Yes, sir. Thank you very much. Why do I what? You like Mickey Mouse so much. Sorry, I didn't get that. Mickey Mouse. Oh, Mickey Mouse. I don't know, maybe when I was growing up and as a kid, and I liked to watch Mickey Mouse run around in the telly in black and white, you know. Nowadays you get him in colour and stuff, but I know I like Mickey Mouse, he's a nice lad. Didn't like Tom.
Okay, thank you very much. We have another presentation now. Also wanted to remind you that at any moment when you like, you can go outside. Right downstairs we have coffee and some snacks. But the next presenter now is Bosko Mulva, and he will be talking about MikroTik in universities.